Hello everyone. In the previous video I think I have shown you the pre-layout simulation of common drain amplifier, right, where the common drain is used as a source follower, right. We have got around zero point 0.7 of gain, right. So in this video I will show you how to do the post layout simulation of common drain circuit by creating the layout, then performing all the steps, that is design rule check, LVS, then back annotating the same, and to verify the post layout simulation results, okay, with considering the parasitic effect. Okay, so then in order to create the layout, what we have to do, we have to go to launch, select layout Excel, right. So a new window will appear. So in this, so we have to go for create new, click OK. So the name, let it be the same, do not change, let it be the cell name, so because from the cell view schematic view I want to view the layout, right. So just click OK. So when you click OK, so layout window will appear. It is just hide and just open it. So this is the layout window. Now in order to generate the NMOS and PMOS or NMOS layouts, because in this circuit we are using both components are NMOS only, right. So what you have to do, we have to go to connectivity. In this, select generate. In the generate, all from source, right. So we are generating all from the source. Just click OK. Now here, so one thing we should concentrate here is while creating or selecting the generate sources, the components you want to generate, right. Here the instant is selected, IO pins are selected, PR boundary is selected. PR boundary is not mandatory, so you can either select or unselect. But here one thing you have to consider is the chain and folds. Okay, so what is the concept of this chain and fold here is, so if you check the common schematic circuit here, the components are same, right. NMOS and NMOS, both the components are same, and the connectivity between NMOS and NMOS is we have common terminal, that is drain, right. Drain and drain is connected. So here if you select the fold option, chain and fold option, right. So here both NMOS and both the NMOS layouts will overlap. That means drain and drain layout, the terminal will be overlapped. So you can see only single NMOS layout with overlapping of drain of NMOS 1 and drain of NMOS 2, right. That means if you select the chain concept or fold option here, so it will overlap itself by assuming the by analyzing the schematic circuit. If you don't select this chain and fold, if you don't select this, so in the layout you can weave the separate layout for NMOS 1 and separate layout for NMOS 2. If you select the fold option, and in the schematic if both the components are same, and the common terminal is interconnected between both the components, then those terminal will overlap, right. I'll just show you how it will overlap. Okay, so what I recommend is, so you can select a fold option so that it will reduce the area, right. If you are using the same components in the circuit, or else if you get confuses means, so you can just unselect this so that you will have a separate layout for both NMOS 1 and NMOS 2. Okay, so that is the one thing you should remember. Fine. So in IO pins, so all the pins are there, so V in V bias all the pins are there. I'll go to create. So in the option I'll just give some small area for pin configuration, label generation. So click OK. So PR boundary, let it be the same, and everything is same. Now click OK. Now if you observe here, right, see NMOS 1 and NMOS 2 are overlapped. Fine. So if you select Shift F, right, now you can see, right, both the NMOS 1 and NMOS 2 are overlapped, right. So if you observe here, see both the NMOS and PMOS are overlapping, right. See the drain of NMOS and drain of PMOS both are, sorry, drain of NMOS and drain of NMOS 2 both are overlapped here, because I have selected fold option. So otherwise, so if you want to weave this separate layout for NMOS1 and NMOS2, you can select the separate layouts, okay, or you can unselect the fold option. Fine. Okay, now we shall go for its connection. Right, first is I have to connect a V in. So just take V in, it will show where you have to connect. Right, so if you take the schematic here, V in is connected to NMOS1, gate of NMOS1. Here the gate is here, it is polysilicon. Right, so this is the NMOS1 polysilicon. Right, so we have to connect this to this point. Right, so how to connect? So I'll just take this pin here. So just extend this polysilicon and connect a V in using contact. Right, so I'll select path P shortcut. So click yes. So take this side. So double click. Now in order to connect this, I need contact, via contact. So I can go to create, select via, or you can shortcut is O. Right, in order to connect this pin, this metal and poly, I need M1 poly contact. Via definition I need this, so I'll select, hide and place it here. So I'll just zoom it and place it here. Okay, now I have not selected this DRD notify, so because of that, so you have to extend this as we have done in both the common source and inverter. So for that, so you have to select this, go to edit, hierarchy, select flatten. Right, this you already know that in order to separate the layer, to create separation of layers, so we have to do this. So select all, so just select all, fine, click OK. Now it is separated, so we have to extend this. Right, so select stretch, shortcut is S, so I'll stretch here. Right, both, see, now the is gone. Fit. Now I'll connect a V in to this pin. Right, now I have placed the pin, so I'll just V in and V out pins on this side. Okay, now V in connection is done. Now I'll give the V bias connection. Right, this is the V bias. See, if you observe here, so this is the V bias. Right, the NMOS 1, NMOS 2 gate is connected to V bias. Right, here in this case, so this is the polysilicon. Either you can extend this side or you can extend on the this side. Right, here we have already extended V in, so I'll extend polysilicon on this side and I'll connect to V bias. Right, so how do we do that? So select path P, select it and extend to this point. Okay, now I have to connect V bias here. So in order to connect V bias, I need via contact. Right, so how to connect? Select P, select O. So via contact is M1 PO. Right, so via contact I have to select, hide and place via contact here. It is also showing the minimum area, so we have to do the extension as we did in V in also via contact. So what we have to do, we have to select this via contact, so flatten it, go into hierarchy and flatten it. Right, now extend it. Right, so how to extend? How to extend? So select stretch, so stretch both. Right, now we have stretched, so now we have to connect the V bias at this point. So remember, these pins will move in both either vertical or horizontal connection, right, direction. So now I have given V bias connection also. Right, so we have done with V in as well as V bias in the common drain circuit. See, V in and V bias we have done with. Now drain and drain is connected, that is connected to V out. Right, we shall give the V out connection by connecting the drain and drain. So because it is created, because it is already created the fold option, so drainer of NMOS1 and drainer of NMOS2 is already overlapped, right? So if you observe here, this is my V out pin, right? So this is my V out pin, right? So if I extend this, see it is showing at this point. So that means, so I have to connect V out to here, right? I'll just take V out in this side, right? So this metal has to be extended and has to be connected to V out, right? So I'll select path. See, it is automatically showing the connection, right? So I'll just take this here. So if I take select and select the path, see it's automatically showing, right? Or you can start from here, path, so select and place it now. So if you ask me here, so why you're passing polysilicon or metal on polysilicon, you can pass it, right? There is no problem with passing the metal on the polysilicon, right? So that will not create a overlap unless you place a contact here. Via contact, if you place it here, it will connect, otherwise it will not connect, right? So we have a free move around this direction. So I've just connected it. Now we have done with V out, so we have left with VDD connection, right? So VDD is connected where? So source of NMOS is connected to VDD, right? Let me take that. So if I move the VDD, it will only show which is the source of NMOS1. So this is this NMOS1, so it has to be connected to, this has to be connected to VDD, right? So if you observe here, this is NMOS, so you can directly connect it to VDD. You don't have to select via NVAL, so as we did in common source as well as common source as well as inverter, because this is NMOS circuit. So for NMOS circuit, in order to give the VDD connection, you can directly give the VDD connection because it is not PMOS. If it is PMOS, you would have created an NVAL, inside that you would have connected the VDD connection. But here in this case it is only NMOS, so you can directly connect it to VDD. Okay, so I'll just take VDD here on this side, because on the bottom side we have already the V out connection, metal is already there, so I'll take it here. Okay, so now I have to connect this to V in, so it is automatically selected, right? If you select here path, see it just extended, it is connecting. Now VDD connection is done, so we left with the VSS connection only. So this is the VSS, so we have to connect across this, right? So and if you observe, this is a NMOS, so if you want to connect the NMOS and source of NMOS to VSS, means you have to connect via P substrate, right? Do not forget that, right? Because you have to connect via P substrate, right? So what you have to do, you have to go to via, so shortcut is O, go to via, here via definition select M1 P substrate, right? To connect via P substrate and come here and place it parallel with this. Okay, so now what you have to do, so because it was showing the minimum area, so as we did in the previous certain experiments, you have to go to edit, hierarchy and flatten it, right? Flatten and click OK. Now so this has been flattened. Now we have to extend this, so extend, select stretch, extend this. So we have to extend the oxide layer, so I'm extending, this is the oxide layer, I'm extending it, so minimum area it has gone. Now what we have to do, we have to connect the source of NMOS 2 to this, right? So how to connect, so select path, P is the shortcut from here to here, right? Before that let me take this VSS proper connection. change this. So just take this outside. Okay, now we have to connect path. So I'll take a path. I'll connect to VDD, sorry, VSS. Right, so I have to connect this pin. So I'll take the pin and place it on the VDD pin. Now if you check here, now I have made all the connections, right? So that is V bias, V in, V out, VDD as well as VSS. Why I have connected only P substrate? Because this is the NMOS. So NMOS to connect to, if you want to connect the NMOS to VSS, you have to connect via P substrate, right? So for VDD connection you don't have to use it. Why? Because it is NMOS, so you don't have to create it within the N-well, because if it is a PMOS you would have created the N-well. Okay, so that's it. So we have created the layout successfully for common drain amplifier. Fine, so it basically works as a source follower. Okay, now just save this. Now what is the next step? So we have to go to Asura, because now to perform the DRC check, right? Before that I'll just ensure that my technology file is selected or not. So it's already selected. So I'll go to Asura, select run DRC, right? So technology is selected, click OK. Now it's running DRC design rule check. So it has run. I'll just view the form. So no DRC error found. Right, I've followed all the rules properly. Now just close it. Now what is the next step? We have to go to Asura. We have to run the LVS, layout versus schematic. Right, click on run LVS. So technology is selected. So click OK. Right, so LVS data is already there. I'll just overwrite it. Right, OK. Click OK. Now so common drain is running the LVS. So if you observe here, so LVS is matched, so no mismatches found, right? I'll just click OK. So it will say schematic and layout are matched, right? Now click OK. So LVS is run successfully. Okay, so I'll just close this. What is the next step? So we have to perform the parasitic extraction, right? So go to Asura, run QRC, right? So in the run QRC, make sure all the things are selected properly. So RCS worked, selected. So AV extracted. So we have unclicked unclicked the LV check. It's already done. Now the extraction, we shall go to extraction RC infinite. So 25 degree. Then the reference node, it is ground. So we already created. In the filtering, so we have created VDD as well as VSS and ground. It's also done. So all those things are done properly. So all the selection are done, right? Settings are done. So now I'll just click OK. Now it is extracting the parasites. Now so it is completed successfully. I'll just close this. So just to for view the layout extraction, so I'll just go to file, open. So in the view, I am viewing the schematic. I want to view the AV extracted file. I'll just select that. Now we can see the AV extracted file. Shift F to view the tiny particles inside this. So you can see all the parasites extracted. Okay. Now I have successfully extracted the AV extraction file. Now what is the next step? We have to back annotate this, right? So in order to back annotate, I just close this. So what we have to do, I have to go to file, new, select cell view. I have to create a new cell view for back annotate purpose, right? That is to create the config file, right? So before that, I'll just ensure that what is the name given for common drain test circuit. So it is common drain test circuit, because you have to give the same name, right? Okay, now go to file, new, cell view. Here give this as common drain test circuit, right? So here, instead of type, instead of layout, select config, right? Open with hierarchy editor. So just click OK. Now here use template. In the template, select spectre or spectre. Just click OK. Now in the my view, so there is a my view is there. Select schematic. Okay. Now just click OK. Now all the test one circuit schematic both are generated. Here in the test circuit, sorry, or in the test or schematic. So view found is in the claim schematic. View found is schematic. I want to view the AV extracted file, right? So AV underscore extracted, you have to select, right? So just select. So it is already selected. The file is there and it is selected. Now it will ask for update needed. Just click on that. Now it is asked for confirmation. Click OK. Now you are successfully back annotated the AV extracted file, right? Instead of a schematic. Now if you observe here, we found is now AV extracted. Just save and close. Now back annotation is done properly. Now in order to perform the post layout simulation, you have to go to file, open the common drain test circuit. In the common drain test, view found is config, let it be the same. Click OK. Now I don't want to configure, but I want to view the cell view. So just no and select yes. Click OK. Now you can see the test circuit used for pre-layout simulation. Now the same thing will be used for post layout simulation, right? Just to verify whether this symbol has the AV extracted file, just select and right click, select this and read. Now if you see, we found is AV extracted. Now inside this we have the AV extracted file. Just I'll just confirm, so just cancel it. Now we have to perform the AC/DC analysis, right, as well as transient analysis, right? So what we have to do, we have to go to launch, select ADEL, analog design environment layout. Fine. Now we can see the environment is open now. So in order to set up all the DC AC analysis, so you can just go to select analysis, you can choose it here, all the things. But because I have saved while doing the pre-out simulations, so I'll just load those states analysis from here, right? So in the session I'll select load state, so I click OK. So automatically it will select all the loads. Okay, otherwise if you have not saved while doing the pre-out simulation, you can just recreate or select all the analysis one more time by going to analysis. You can choose all the analysis one more time. Otherwise, if you would have selected, you can select, you can save, or you can load directly from here. Okay, fine. So now let's just run from here with the parasitic effects. Now I can see the simulation results. Fine. So I'll take the sub windows. Fine. So this is my transient analysis. Fine. Okay, I'll just select this, or this is the transient analysis. Okay, so this is AC analysis and this is DC analysis, right? If you observe, right, in the pre-layout simulation we had got, because it's a source follower, we have got around 7 millivolts, right, peak to peak, for 10 millivolts peak to peak. So it is almost equal, right? So what is the gain is around 0.7, right? So that is without the consideration of parasitic effect. Now we are considering parasitic effect here, right, with RC components. So here if you calculate, so this is 2.897 minus 2.903, right? If you select, if you calculate 2.907 minus, sorry, 2.903 minus 2.897 minus 2.897, so you get 0.006 volts. So that means around 6 millivolts you will get. That means, so with the consideration of parasitic effect, so around 1 millivolts has been lost, right? So that is the difference in pre-layout as well as post-layout simulation. That means you were expecting in the schematic, you are expecting the 7 millivolts of peak-to-peak voltage, right, in the output, but here you are getting 0.6 millivolts. That means there is a slight difference in the gain. That means around you are getting zero point 0.6 gain, right? So that is with consideration of pre-layout, sorry, with consideration of parasitic effect, right? So that is what, so you have to analyze, you have to compare pre-layout as well as post-layout simulations, right? Now, so if you want, higher, at least, near to the pre-layout simulation results, so you have to go back, to your layout, and you have to perform, the area optimization uh, things once again. Then you have to come back and you have to perform the simulation results again, right, by extracting the parasites, so you may get the higher results or expected results. Okay, so what you have to do, so once you have got the results, so just print this file, right? So in the test VLSI, I think I need that inside the test one, right? Here I'm saving all those, so I'll save that as, so this is CD post layout results, right? I'll just save this and print. Now it has saved all the data with a PDF file. Okay, so this is the post layout simulation of common drain, right? With respect to pre-layout and post layout simulation, you have a 0.001 or zero point 0.1 slight difference in the gain with consideration of parasitic effect, so that you have to note down all the values in the pre-layout as well as post-layout simulation, then you have to compare it for the optimization purpose. Okay, so thank you. Now you can see, I'll just show you that file also, so we'll just compare that for a moment. So in the test VLSI, I have in test 1, see, common drain pre-layout and post-layout simulation both are here. In the pre-layout simulation, if you observe here, this is the peak-to-peak voltage. So if you take here, so this is 2.917, so minus, so here the gain you got around 0.653 or 0.653, right? But in post layout simulation, you've got, so you have got around point, sorry, this is the post layout simulation, yes, yeah, around 6.658. That means the gain is almost reduced. Fine, so around zero point 0.1 millivolts has been reduced in the gain. So that is what is all about the common drain pre-layout as well as post layout. Okay, thank you.